期中考之后就开始有同学要停休了，所以他今天这个班上，有10个人吧，10多个啊，可能跟天气也有关系啊，下雨，不然就是要准备要停休了。我看应该只有一个。We have only 4 students in this class. I think you're the only one right now. So actually we can, well, we still have to use English. Okay, so let's review last week's content about this transient enhanced diffusion. I think for the eye implantation, there are 2 important characteristics. One is we need to understand how the eye implantation works in your implantation process, and also what's the kind of effect. Because other for like diffusion process, that will be similar as last chapter. Okay, but this TED can only be seen in these eye implantations when you do the healing process. Okay. So okay, so this transient enhanced diffusion is caused by the interstitial damage. Okay, resulting from the implantations, because you try to use iron to bombard your second substrate, and that will create some damage, and those interstitials defects, okay, is I+1. Okay, now that interstitials will help the dopant, okay, help them to diffuse faster. Sometimes, especially at low temperatures. Okay, so it's quite a dominant effect when we talk about eye implantations, especially when we try to reach shallow junctions. Then this may cause a problem. Okay, so we can see from these figures, under the same diffusion constant times T. Okay, we call this thermal budget. This under the same dt. You can see this for lower temperatures one, these red curves. You can see the dopant will diffuse deeper into your substrates. It's quite different from what our intuitions. Right? We think that in the diffusion chapter, we know that when we increase the temperature, the dopant can diffuse faster. But in here, you can find out that under 800 degrees C, you will see the dopant will diffuse deeper into your material. Okay, so that's because because you have an implantation that creates those damage, and those damage can help you. Will form a kind of a new species with dopant, so that can move faster with higher diffusion constant. So, because at lower temperatures, those interstitials can exist longer than they are at higher temperature. Because when we increase the temperature, when we do the kneading, those defects can recombine quickly. Right? But for lower temperature, the recombination rate will be slower, and so those defects can exist longer. Things they can exist longer, so they can combine with those dopant and form new species and move together. So that's the enhanced diffusion caused by this interstitial defect. Okay, so you can see that at lower temperature, the enhancement factor is even higher at higher temperatures, and so that's quite significant. So we can use that this kind of effect is very important when we discuss the eye implantations. Okay, and this TED very non-local. Okay, so this is a profile that we have a boron profile. It's a berry layer underneath your surface. And when we do the arsenic implantation, and so we create the amorphous and crystal lines here, and this is arsenic profile. Then when we do this annealing, let's say 900 degrees C in 1 second, then we can make this amorphous arsenic surface profile to recrystallize, okay, by the solid phase epitaxy without much TED. But we all have this +1 interstitials that will move faster to the dopant, and they can help this boron to out diffuse quickly. So you can see this green line is the final profile. As this arsenic, they will change a lot, but for boron, okay, you can see these tails, okay, as a result of your TED. So it can be very non-local. Okay, and here are 4 lines with these experimental data at different temperatures. So on this y-axis is the interstitial defect density, and this is time in seconds. Okay, so in the beginning we have this +1 defect that will form in the cluster at these 311 planes. Okay, and those clusters will begin to emit or inject these interstitials. Okay, so by emitting that, the cluster can be shrink, like become like smaller and smaller in volume. But when they inject these interstitials, that will increase the supersaturation of your interstitial concentrations. Okay, and those will create, if you have more those interstitial supersaturation concentration, if you have more of that, then you can see the more pronounced TED. Okay, so so from here you can see this defect density will drop when we increase this increase our time, annealing time, right? And at lower, at higher temperature, like this red curve, you can see that within that shorter time, then you can reduce this defect density to maybe 10 to 11 the level. Okay. So that's because they will begin to recombine and make these clusters smaller and smaller. Okay, but for lower temperature, like this 670 degrees C, you can see that the time scale is much larger compared to the high temperature. So it tells that those interstitial defects can exist longer at lower temperatures. Okay, but they will be reduced to that very low level at a shorter time if we increase the temperatures. Okay, and also there's the interstitial damage with the profile, okay, with this depth in micron. So that's in the beginning we have a lot of damages, maybe to 10 to 18 to 19. Okay, so then once those damages are generated in the beginning, in a very shorter time, like in microseconds, they begin to recombine. Okay, they have some local recombination or surface recombinations, and your vacancy cluster will shrink. Okay, by emitting this +1 interstitials, and So this is when you see when the time continues to maybe 10 into the minus 1, which is 0.1 seconds. Okay. Those you can see this supersaturation concentration will reach to a constant level of like 10 to 13. Okay, and at that time your defects already formed, and you can see this CI is interstitial concentration 10 to 13. Okay, and if we compare with the normal concentration at 750, the CI is usually at 10 to the 8. Okay, but here is after implantation. So you can see that the enhancement factor is larger than like 100,000 here. Okay. So when we increase the time, you can see this concentration continue to drop. Okay. The decrease of this concentration is due to the ejection of this interstitial defect. Okay, so we can use this atomic level insights to explain this TED. Okay, so we can consider that if we have one eye and we have a cluster with N interstitials. Okay, so this eye can join this N clusters and form this N+1 cluster here. Okay, and you can do the opposite way. Okay, by ejecting one eye here. Okay, so we can take this. We can see this concentration change rate here. I take the differentiation of this CI time. Okay. So if you have a one CI reduced, and that will corresponds to the cluster increase. Okay. So when we talk about this cluster increase, we can write this two components. One is the cluster to growth. One is cluster to shrink. Okay. Cluster to growth is to go to the right hand side. So we will have this Kf, this forming constant with this Ci here, the concentration of this I and the concentration of this cluster. Okay, but when we go to the left hand side, that's the recombination, or because due to this recombination, we will reduce this I. So cluster will begin to shrink. Okay, so this is very intuitive expressions for this from the chemical reaction point of view. Okay, and then we try to calculate this effective diffusion constant. Okay. But we neglect some derivation. If you're interested, you can check the textbook. Okay, so this is the diffusion constant that I think we saw this. We saw this before, right? And we have the different parameters here. And then we can calculate this in a steady state. Okay, so the cluster growth and the sequence evaporation, they can reach balance. Okay, so the net rate change is zero. So we take this one as a steady state. We can solve this in this equation 21. Okay, this gives us this CI concentration. Okay, so we can plot this line here as a function of temperatures. Okay. Okay, so from this equation we can plot these figures. Okay, and also this diffusivity enhancement can be as large as 10,000 at low temperatures and falls to 100 to 1,000 at RTA temperatures. Okay, and this figure shows the boron TED by simulation. Okay, so this blue line is the original implantation profile of this boron profile as implanted. Then when you do the annealing in 1 minute at 750 degrees C, you can see the profile begin to diffuse as this black line, and this black dashed line is the concentration profile, which you can see from. Okay, so this is the concentration profile. Okay, and this is the enhancement factors here. Okay. Oh no, sorry. This is the ratio. Okay, this is the ratio of this ratio. Okay, so this ratio originally we can consider that as the enhancement factor, right? Okay, so it's like 10,000 and down to like 100 when we increase the time from 1 minute to 10 minutes at 750 degrees C. So we can see that when we increase the time, those interstitials begin to recombine. Okay, with those vacancy clusters. So this is the red curve. You can see the final boron profiles and the final those concentration profile. Okay, and the concentration profile, you can see that goes to very low level, close to the surface. Okay, that's because you have more surface recombination happens in this process. Okay, so I think the important figure of memories of this figure is this curve. Okay, you can see this super saturation of our interstitial concentration drops when we increase the time due to this I and V recombination process. Okay, and now we can use these figures to explain the surface recombinations. So at a certain implantation dose and energy level, this is RP. Okay, so you have total dose Q, and that will create a diffusion flux going to this way and also goes to this way. And because we have surface recombination, so that will make this flux drops quickly. So you can see this slope is quite different of these two fluxes. Okay, and the flux to the surface can be written like this. And we have this diffusion constant and this concentration divided by the range of the implant. So that's the flux to the surface. And the time to dissolve the clusters, okay, is given by the flows divided by the flux. Okay, so this is another result of this TED that we are interested in is the time of the enhancement. Okay, so we can plot this at these figures. Okay, so you can see that at lower temperatures, the time of enhancement is quite large. Okay, which means that those TED process can exist longer compared with the one at higher temperatures. Okay. So like even for hours at low temperatures. But if you're near at high temperatures, okay, it can drop to maybe less than 1 second. Okay. Okay, so we draw this general picture to summarize the TED process. Okay, so this is the enhancement. So the CI max divided by the CI start. Okay, so we have this, in the beginning, we have like 10,000 enhancement factors. Okay, and this is the time of the enhancement. And this blue one is the cluster. You can see the cluster begin to shrink, okay, when we increase the annealing time. So you can see these blue lines become shorter and shorter. So that means this cluster begin to decay, okay. And during this time of enhancement, we see that this CI max still remains a very large, very high level, and then they quickly drop exponentially. Okay, so that's these pictures give us some idea and try to summarize the TED process. We have these clusters and they can provide the interstitials, and when we increase the annealing time, those clusters begin to shrink, to decay. Okay, so we can recombine with these interstitials. And during this supersaturation time region, and you can see the TED enhancement can be quite large to like 10,000, and it begin to drop exponentially. Okay, and on the right hand side, we can see how does that affect our profile, okay, our diffusion profile. Okay. So the black one is the originally profile as implanted, and we have 3 different temperatures for our annealing process. Well, 700, 800, and 900. Okay, so it's quite interesting. You can see at 900 degrees C, the diffusion profile, the diffusion depth is the smallest one. And the one for 700 degrees C, the depth is the largest. So that's because of our these supersaturation ratios. For 700 degrees C, you can see this your interstitial defect can exist longer, and the ratio is larger, so that causes the enhancement factors to increase your diffusion constant. Okay, so it's quite different than previously we have talked about the diffusion process. Okay, you see that at lower temperature you even have a larger diffusion profile. That's because of those defects. Okay. Okay, so here are two figures. Okay, the figures on the top is the energy dependence of TED. Okay, so when we increase the energy, okay, so we can expect more damage in our material. Okay, so you can see the TED will become larger. Okay, because at that time your surface is not a dominant thing. Okay, this things means you seek for the interstitial damages. Okay, so that's a sink or drain, for the damage to go or to recombine there. Okay. And this is a DT. Okay, so you can consider that as like a diffusion factors. Okay, so at lower temperatures you can see more profiles or more deep profile you can observe because you have a larger DT at lower temperatures. And also when you increase this energy, you have create more damages, so you can see this DT will increase. Okay, so that's you can see from these figures. And the figure below here shows the dependence of your dose. Okay. So when we increase the dose, okay, so at low temperature, we didn't see much difference. But when we increase the annealing time, you will begin to see for those higher dose. Okay, so we have more pronounced TED effect. So you see the diffusion distance begins to increase for higher dose. Okay, and for the lower dose, because the cluster it might be already annealed. Okay, so you can see this one doesn't change that much. Okay, when we increase this time from 100 to 1,000 seconds. Okay, and for shorter time here, okay, you can see the TED is the same for all those, because at that time you still have clusters that can continue to supply I. So you didn't see much difference between them. Okay, and the effect on the devices, the figure on the left hand side is the same figures that I think we have seen in the diffusion in the last chapter. Okay, so we do the source strand annealing here, and that will provide this excess I. And this I will diffuse into the channel. Okay, so they will diffuse into the channel. And pushing your boron dopant, okay, your channel dopant up toward the surface. Okay, and this effect is more pronounced in smaller devices. When you try to shrink the source strain or the gain length, okay, they become more pronounced. So when we reduce this gain length, you can see that the channel, this concentration will increase, and that will cause your VT to increase for shorter channel. Okay, that's what we call this reverse source short channel effect. It's reverse short channel effect because your channel dopant will pass up at the surface, and that's due to the effect of your interstitials. And those interstitials generated from your source strain implant. Okay, so that's the effect on devices. Okay, so now here's a summary of this chapter. Okay, so eye implantation can provide great flexibility and excellent control of dopant. Okay, and our implanted eye energy is larger than silicon binding energy. So you can expand your lattice. If those atoms are displaced, then you create a lot of damage by these incoming ions. And this damage can accumulate with your implant dose and make your crystal become amorphous. Okay, but we can use a kneading process to recover those amorphous region. Okay, and also we worry about some channeling effect. Okay, and so that will we try to maybe rotate or use different angle or put on amorphous silicon nitride or silicon oxide on top of your silicon before we do the implantations. And the biggest problem for implantation is this TED, okay? Because that leads to a huge enhancement in your dopant diffusivity. Okay, then we use some atomic label to explain and to understand the TED process, and that gives us a way to control it by this RTA annealing. Okay, so in the future, these shallow junctions will be a challenge, but we can use this RTA to control, or like different advanced annealing technologies. Okay, some maybe use like laser to do the locally annealing. Okay, so that's the implantations. Let's move on to this chapter 9. We talk about thin film. Okay, how can we deposit